apologize. I have a cold, so I hope you can hear me. My name is Johanna Mathieu, and I'm an assistant professor in electrical engineering and computer science, but I'm on the electrical engineering side of the department. So today I'm going to tell you about...
Sorry.
I'll stop all this. Today I'm going to tell you about my work, which is to use household appliances and buildings, including University of Michigan buildings, to support renewable energy integration. Okay, so I have a bunch of boring slides because I'm an engineer. I don't have as many pictures, but I also don't have any equations. I made sure not to put any in. My work generally looks at trying to improve the sustainability of the electric power grid, also the economics of the grid, and the reliability of the grid. And what I do is create algorithms to help control and operate and optimize the power system, the electric power system. And specifically, I'm interested in using distributed energy resources. So those are things like energy storage and flexible electric loads to help integrate renewable energy like wind and solar. So wind and solar produce whenever they want to produce. We can't control them. And so from that perspective, power systems engineers, and I call myself one of them, we don't like these resources as much because they're not as controllable. But we do realize that they're very important because of all their other benefits. So how can we integrate them as well as possible by balancing their renewability, the variability with other resources that might be flexible in terms of when they produce power or when they consume power. So a lot of my work looks at trying to create energy storage where it doesn't already exist by harnessing storage that's already in the grid, because there actually is a lot of storage that exists in the grid, but we're not using it as storage. There's very few grid-sized batteries that exist, almost none. There are some facilities like pumped hydro facilities. Michigan has one where we pump water uphill and then pump it back downhill, and it's basically a big water battery, but there's very few batteries in the grid, so supply and demand have to be matched at all times. So my work is to try to figure out how to get storage from what we got. And a lot of that storage isn't electrical storage, it's thermal storage. So I just have a few slides on my research because I thought I was only able to speak for 3 minutes. So this is one example I will talk about. It's coordinating the power consumption of residential appliances. The types of appliances I'm talking about are things, we call them thermostatically controlled loads, but they're your refrigerators, your water heaters, and your air conditioners that are in your houses. And what we're trying to do is coordinate their power consumption. So I'll take thousands of them across the network and slightly change the timing of their switchings on and off so that customers don't notice and the temperature is still within the normal range. But to do that, when I do that in my work, what I can see is that you can control their power consumption to basically balance the variability of renewables. So over there showing that's the power consumption we need to balance renewables, and this is what we can achieve when we coordinate these resources by sending them control signals. And the work we actually do and that we publish on is developing the methods, which include things like state estimation, controller design, optimization algorithms, and trying to do that in a way where you don't need a lot of fancy communication networks because they're expensive. So that's one project I work on. Another project, which touches campus a little bit more and is more linked to this topic because we're looking at the built environment, is using buildings on campus as thermal batteries. So we've been working with these 3 buildings over the last year or two and controlling their HVAC system, so the HVAC system, the heating, ventilation, air conditioning system, changing temperature set points in these buildings by very small amounts, a degree or 2, in a direction just for a few minutes and then back again. So no one in the building notices, but the building's power consumption changes. And what we're doing with that is when wind power goes away, we decrease the consumption, and when it comes back, we increase the consumption to better match when wind is producing in Michigan. So we're doing these tests, and we're trying to understand how the building responds. And we're designing these tests to be energy neutral in the sense that if we change it in the building in one direction, we want to change it back. So over the day, it consumes the same amount of energy as before. It's just shifting when it's happening to better match renewable production. But what we find is when we do this to buildings, the buildings actually want to consume a little bit more power than they would have otherwise. So we model them as a battery, and we find that they're inefficient battery. There's losses, round-trip losses. You put energy in, you get a little bit less out. So we're trying to understand this, and we're actually finding that the inefficiency is pretty extreme. So most batteries are like 80 to 90% efficient. Buildings are 40 to 60% efficient. But we think that we can fix it because we think that the control systems that are operating the buildings are the problem and that we can fix that. So that's what I work on. So just to give you an idea, I collaborate with a variety of folks in engineering and at national labs, but I also have collaborations with people in SEAS and public policy. And I also work with the electric utilities like DTE. I teach a variety of courses in electrical engineering, and I have C students take my courses. They usually start with this power systems design and operations course. Most of them have engineering backgrounds. but from all different sorts of engineering, and they take that course, and then that introduces them to the other areas. And we also have been developing these sort of short courses that are available, that we sometimes give, that are available to anybody on campus, just to understand how the grid works and how their research could plug into ours. Thanks.